Chapter 6. Superposition of waves. Exercises pages 156 to 157. Exercises Q1.1, page 156. Choose the correct option. When an air column in a pipe closed at one end vibrates such that three nodes are formed in it, the frequency of its vibrations is _ times the fundamental frequency. 1, 2, 2, 3, 3, 4, 4, 5. Solution. When an air column in a pipe closed at one end vibrates such that three nodes are formed in it, the frequency of its vibrations is 5 times the fundamental frequency. Exercises Q1.2, page 156. Choose the correct option. If two open organ pipes of length 50 cm and 51 cm sounded together produce 7 beats per second, the speed of sound is 1. 307 meter per second, 2. 327 meter per second, 3. 350 meter per second, 4. 357 meter per second. Solution. 357 meters per second. Exercises Q1.3, page 156. Choose the correct option. The tension in a piano wire is increased by 25%. Its frequency becomes _ times the original frequency. 1. 0.82. 1.123. 1.254. 1.56. Solution. The tension in a piano wire is increased by 25%. Its frequency becomes 1.12 times the original frequency. Exercises Q1.4, page 156. Choose the correct option. Which of the following equations represents a wave traveling along y-axis? 1. X equals a sin ky omega t. 2. Y equals a sin kx omega t. 3. Y equals a sin ky cos omega t. 4. Y equals a cos ky sin omega t. Solution. X equals a sin ky omega t. Here x is the particle displacement of the wave and the wave is traveling along the y-axis because the particle displacement is perpendicular to the direction of wave motion. Exercises Q1.5, page 156. Choose the correct option. A standing wave is produced on a string clamped at one end and free at the other. The length of the string. Solution. A standing wave is produced on a string clamped at one end and free at the other. Its fundamental frequency is given by Exercises Q2.1, page 156. Answer in brief. A wave is represented by an equation y equals a sin bx plus cort. Given that the constants a, b and c are positive, can you tell in which direction the wave is moving? Solution. Equation of the wave is y equals a sin bx plus cort. When the variable of the equation is bx plus cort, then the wave must be moving in the negative x direction. Exercises Q2.2, page 156. Answer in brief. A string is fixed at the two ends and is vibrating in its fundamental mode. It is known that the two ends will be at rest. Apart from these, is there any position on the string which can be touched so as not to disturb the motion of the string? What will be the answer to this question if the string is vibrating in its first and second overtones? Solution. No. We know that in case of the fundamental mode, all points except the ends are vibrating with different amplitudes. Now, touching any point other than the ends will disturb the motion. When the string will vibrate in the first overtone, there is a node also at the midpoint which is stationary. This midpoint can be touched without disturbing the motion. Thus, we can say that there is no point in the string that can satisfy the given condition. Exercises Q2.3, page 156. Answer in brief. What are harmonics and overtones? Solution. Harmonic frequencies are whole number multiples of the fundamental frequency or the lowest frequency of vibration. Consider a vibrating string. The modes of vibration are all multiples of the fundamental, and are related to the string length and wave velocity. Higher frequencies are found via the relationship Fn equals Nf1, wavelength equals where L is the string length. An overtone is a name given to any resonant frequency above the fundamental frequency or fundamental tone. The list of successive overtones for an object is called the overtone series. The first overtone as well as all subsequent overtones in the series may or may not be an integer multiple of the fundamental. Sometimes the relationship is that simple, and other times it is more complex, depending on the properties and geometry of the vibrating object. Exercises Q2.4, page 156. Answer in brief. For a stationary wave set up in a string having both ends fixed, what is the ratio of the fundamental frequency to the second harmonic? Solution. The fundamental is the first harmonic. Therefore, the ratio of the fundamental frequency n to the second harmonic n1 is 1:2. Exercises Q2.5, page 156. Answer in brief. The amplitude of a wave is represented by y equals 0.2 sin 4 pi. In SI units, find a wavelength, b frequency, and c amplitude of the wave. Solution. Exercises Q3, page 156. Answer in brief. State the characteristics of progressive waves. Solution. Progressive wave. A progressive wave is defined as the onward transmission of the vibratory motion of a body in an elastic medium from one particle to the successive particle. Characteristics of a progressive wave. Energy is transmitted from particle to particle without the physical transfer of matter. The particles of the medium vibrate periodically about their equilibrium positions. In the absence of dissipative forces, every particle vibrates with the same amplitude and frequency but differs in phase from its adjacent particles. Every particle lags behind in its state of motion compared to the one before it. Wave motion is doubly periodic, i.e., it is periodic in time and periodic in space. The velocity of propagation through a medium depends upon the properties of the medium. A transverse wave can propagate only through solids, but not through liquids and gases, while a longitudinal wave can propagate through any material medium. Progressive waves are of two types, transverse and longitudinal. In a transverse mechanical wave, the individual particles of the medium vibrate perpendicular to the direction of propagation of the wave. The progressively changing phase of the successive particles results in the formation of alternate crests and troughs that are periodic in space and time. In an M wave, the electric and magnetic fields oscillate in mutually perpendicular directions, perpendicular to the direction of propagation. In a longitudinal mechanical wave, the individual particles of the medium vibrate along the line of propagation of the wave. The progressively changing phase of the successive particles results in the formation of typical alternate regions of compressions and rarefactions that are periodic in space and time. Periodic compressions and rarefactions result in periodic pressure and density variations in the medium. There is no longitudinal M wave. Exercises Q4, page 156. Answer in brief. State the characteristics of stationary waves. Solution. Stationary wave. When two identical, progressive waves of equal amplitudes and equal wavelengths and traveling in a similar medium, along the similar straight line, but in opposite directions, interfere, and then the wave formed is called a standing wave or a stationary wave. Characteristics of stationary waves. 1. Stationary waves are produced by the interference of two identical progressive waves traveling in opposite directions, under certain conditions. 2. The overall appearance of a standing wave is of alternate intensity maximum, displacement antinode, and minimum displacement node. 3. The distance between adjacent nodes, or antinodes, is lambda 2. 4. The distance between successive node and antinode is lambda 4. 5. There is no progressive change of phase from particle to particle. All the particles in one loop, between two adjacent nodes, vibrate in the same phase, while the particles in adjacent loops are in opposite phase. 6. A stationary wave does not propagate in any direction and hence does not transport energy through the medium. Exercises Q5, page 156. Derive an expression for the equation of stationary wave on a stretched string. Solution. When two progressive waves having the same amplitude, wavelength and speed propagate in opposite directions through the same region of a medium, their superposition under certain conditions creates a stationary interference pattern called a stationary wave. Consider two simple harmonic progressive waves, of the same amplitude A, wavelength lambda, and frequency n equals omega, 2 pi, traveling on a string stretched along the z-axis in opposite directions. They may be represented by y1 equals a sin omega t, kx along the plus z-axis and 1. y2 equals a sin omega t plus kx along the minus z-axis. 2. Where k equals 2 pi lambda is the propagation constant. By the superposition principle, the resultant displacement of the particle of the medium at the point at which the two waves arrive simultaneously is the algebraic sum. Y equals y1 plus y2 equals a sin omega t, kx plus sin omega t plus kx. Exercises Q6 page 156. Find the amplitude of the resultant wave produced due to interference of two waves given as y1 equals a1 sin omega t, y2 equals a2 sin omega t plus phi. Solution. The amplitude of the resultant wave produced due to the interference of the two waves is. Exercises Q7 page 156. State the laws of vibrating strings. Solution. The fundamental frequency of vibration of a stretched string or wire of uniform cross-section is. Exercises Q8 page 156. Show that only odd harmonics are present in an air column vibrating in a pipe closed at one end. Solution. Consider the different modes of vibration of an air column within a pipe closed at one end. Let L be the length of the pipe. Stationary waves are formed within the air column when the time taken by the sound waves to produce a compression and rarefaction becomes equal to the time taken by the wave to travel twice the length of the tube. The standing waves are formed only for certain discrete frequencies. In the first mode of vibration of the air column, there is one node and one antinode as shown in the figure above. If lambda is the length of the wave in the fundamental mode of vibration, then, length of the air column, L equals lambda 4. Rightwards double arrow lambda equals 4L. 1. As velocity of the wave, v equals n lambda. N equals v lambda. Substituting 1, we get n equals v 4L, frequency of the fundamental mode. In the second mode of vibration of the air column, two nodes and two antinodes are formed. In this case, the length of the air column, L equals 3 lambda 1/4. Where lambda 1 is the wavelength of the wave in the second mode of vibration. Rightwards double arrow lambda equals 4L 3. 1. V equals N1 lambda 1. N1 equals V lambda 1. Substituting 1, we get. This frequency is called the third harmonics or first overtone. Similarly, during the third mode of vibration of the air column, 3 nodes and 3 antinodes are formed. Here, the length of the air column, L equals 5 lambda 2/4. Where lambda 2 is the wavelength of the wave in third mode of vibration. Rightwards double arrow lambda 2 equals 4L 5. 1. V equals N2 lambda 2. N2 equals V lambda 2. Substituting 1, we get. This frequency is called the fifth harmonic or second overtone. Thus, we see that the frequencies of the modes of vibrations are in the ratio n1, n2 equals 1, 3, 5. This shows that only odd harmonics are present in the modes of vibrations of the air column closed at one end. Exercises Q9 page 156 with a neat labeled diagram, show that all harmonics are present in an air column contained in a pipe open at both the ends. Define end correction. Solution. Stationary waves are produced due to the superposition of two identical simple harmonic progressive waves traveling through the same part of the medium in opposite direction. In the case of pipe open at both ends, the air molecules near the open end are free to vibrate, hence they vibrate with maximum amplitude. Therefore the open end becomes an antinode. The simplest mode of vibration is the fundamental mode of vibration. In above Fig. A, in this case one node and two antinodes are formed. If λ1 be the corresponding wavelength and the next possible mode of vibration is called the first overtone. In above Fig. In this case, two nodes and three antinodes are formed. If λ2 and n2 be the corresponding wavelength and frequency, the next possible mode of vibration is called second overtone. In above Fig. C, in this case three nodes and four antinodes are formed. If λ3 and n3 be the corresponding wavelength and frequency, thus in case of pipe open at both ends, all harmonics are present. In this case, the node is forming at the closed end, i.e. at the water surface, and antinode is forming at the open end. But antinode is not formed exactly at the open end but slightly outside it, since air molecules are free to vibrate. The correction has to be applied is called end correction. Exercises Q10, page 156. A wave of frequency 500 Hz is traveling with a speed of 350 meters per second. 8. What is the phase difference between two displacements at a certain point at times 1.0 milliseconds apart? B. What will be the smallest distance between 2 points which are 45 degrees out of phase at an instant of time? Solution. Exercises Q11, page 157. A sound wave in a certain fluid medium is reflected at an obstacle to form a standing wave. The distance between two successive nodes is 3.75 centimeters. If the velocity of sound is 1500 meter per second, find the frequency. Solution. Exercises Q12, page 157. Two sources of sound are separated by a distance of 4 meters. They both emit sound with the same amplitude and frequency, 330 Hz, but they are 180 degrees out of phase. At what points between the two sources will the sound intensity be maximum? Solution. Directly at the center of two sources of sound, path difference is 0. But since the waves are 180 degrees out of phase, two maxima on either side should be at a distance of λ4 from the point at the center. Other maxima will be located each λ2 further along. Thus, the sound intensity will be maximum at plus or minus 0.25, plus or minus 0.75, plus or minus 1.25, plus or minus 1.75 meters from the point at the center. Exercises Q13, page 157. Two sound waves travel at a speed of 330 meters per second. If their frequencies are also identical and are equal to 540 Hz, what will be the phase difference between the waves at points 3.5 meters from one source and 3 meters from the other if the sources are in phase? Solution. Exercises Q14, page 157. Two wires of the same material and the same cross-section are stretched on a sonometer. One wire is loaded with 1.5 kilograms and another is loaded with 6 kilograms. The vibrating length of the first wire is 60 centimeters and its fundamental frequency of vibration is the same as that of the second wire. Calculate the vibrating length of the other wire. Solution. Exercises Q15, page 157. A pipe closed at one end can produce overtones at frequencies 640 Hz, 896 Hz, and 1152 Hz. Calculate the fundamental frequency. Solution. The difference between the given frequencies of the overtones is 256 Hz. This implies that they are consecutive overtones. Let NC be the fundamental frequency of the closed pipe and NQ. NQ1 equals the frequencies of the QTH, Q plus 1 TH and Q plus 2 TH consecutive overtones, where Q is an integer. Data. NQ equals 640 Hz. NQ1 equals 896 Hz, NQ plus 2 equals 1152 Hz. Since only odd harmonics are present as overtones, NQ equals 2Q plus 1 NC, and NQ plus T equals 2Q plus 1 NC equals 2Q plus 3 NC. Therefore, the three given frequencies correspond to the second, third and fourth overtones, i.e., the fifth, 7th and 9th harmonics, respectively. Therefore 5 NC equals 640, therefore BC equals 128 Hz. Exercises Q16, page 157. A standing wave is produced in a tube open at both ends. The fundamental frequency is 300 Hz. What is the length of the tube? Speed of the sound equals 340 meters s1. Solution. Data. For the tube open at both the ends, N equals 300 Hz and B equals 340 meters s1. Ignoring end correction, the fundamental frequency of the tube is. Exercises Q17, page 157. Find the fundamental, first overtone, and second overtone frequencies of a pipe, open at both the ends, of length 25 centimeters if the speed of sound in air is 330 meters per second. Solution. Data. Open pipe, L equals 25 centimeters equals 0.25 meters, V equals 330 meter per second. The fundamental frequency of an open pipe ignoring end correction. Exercises Q18, page 157. A pipe open at both the ends has a fundamental frequency of 600 Hz. The first overtone of a pipe closed at one end has the same frequency as the first overtone of the open pipe. How long are the two pipes? Solution. Data. Open pipe, no equals 600 Hz, NC, 1 equals no, 1 first overtones. For an open pipe, the fundamental frequency. The length of the pipe open at both ends is 27.5 centimeters and the length of the pipe closed at one end is 20.6 centimeters. Exercises Q19, page 157. A string 1 meter long is fixed at one end. The other end is moved up and down with frequency of 15 Hz. Due to this, a stationary wave with 4 complete loops gets produced on the string. Find the speed of the progressive wave which produces the stationary wave. Hint. Remember that the moving end is an antinode. Solution. Data. L equals 1 meter, N equals 15 Hz. The string is fixed only at one end. Hence, an antinode will be formed at the free end. Thus, with 4.5 loops on the string, the length of the string is. Exercises Q20, page 157. A violin string vibrates with fundamental frequency of 440 Hz. What are the frequencies of the first and second overtones? Solution. Data. N equals 440 Hz. The first overtone, N1 equals 2, N equals 2x 400 equals 880 Hz. The second overtone, N2 equals 3, N equals 3x 400 equals 1320 Hz. Exercises Q21, page 157. A set of 8 tuning forks is arranged in a series of increasing order of frequencies. Each fork gives 4 beats per second with the next one, and the frequency of last fork is twice that of the first. Calculate the frequencies of the first and the last fork. Solution. Data. N8 equals 2 N1, beat frequency equals 4 Hz. The set of a tuning fork is arranged in the increasing order of their frequencies. Therefore N2 equals N1 plus 4. N3 equals N2 plus 4 equals N1 plus 2 times 4. N4 equals N3 plus 4 equals N1 plus 3 times 4. Therefore N8 equals N7 plus 4 equals N1 plus 7 times 4 equals N1 plus 28. Since N8 equals 2N1, 2N1 equals N1 plus 28. Therefore the frequency of the first fork, N1 equals 28 Hz. Therefore the frequency of the last fork, N8 equals N1 plus 28 equals 28 plus 28 equals 56 Hz. Exercises Q22, page 157. A sonometer wire is stretched by the tension of 40 N. It vibrates in unison with a tuning fork of frequency 384 Hz. How many numbers of beats get produced in 2 seconds if the tension in the wire is decreased by 1.24 N? Solution. Exercises Q23, page 157. A sonometer wire of length 0.5 meters is stretched by a weight of 5 kilograms. The fundamental frequency of vibration is 100 Hz. Calculate the linear density of wire. Solution. Exercises Q24, page 157. The string of a guitar is 80 centimeters long and has a fundamental frequency of 112 Hz. If a guitarist wishes to produce a frequency of 160 Hz, where should the person press the string? Solution.